Hello, great to be here. Last time it was 3.5 years ago in Rome, where I was able to attend, but after that, Europe User Group meetings were held in the Midsummer Festival in Finland, so that's the time when Finns can't travel. I didn't get a permission from home to travel, but now it's better than now. It's a week before that one. In this presentation, I try to paint a picture about some basics or fundamentals of the 100% renewable power systems. So what kind of optimal capacity mix that would be. This is not going to be a kind of solution for all the systems, but just some ideas that how the systems in the future could look like. Few words about Warsila, the company where I'm coming from. So Warsila has two divisions, Warsila Marine, which is providing solutions for marine industry, and the Warsila Energy, where I'm coming from, where we provide solutions for energy business. It's a global business, so we have approximately 5,000 people in this energy business, 180 locations and 60 countries. Installed base, so the power plants we sell, they are based on engines. It's not a turbine power plant, the similar kind of power engines that are using in the ships. And the installed base for the power plants globally, it's 70 gigawatts all over the globe, where the biggest unit in Jordania actually is 600 megawatts. So it's not a small scale power plants, but also in the utility scale business, pretty much. What comes to Warsila and Plexos, so we have done, as Tom mentioned, that we have quite a lot of modeling cases all over the world, different countries, power systems, and we have used Plexos since 2010. So this gives us some background also that what is actually the value of flexibility, which is the main I would say driver to do the modeling. So value the flexibility in different power systems. And based on these country and the power system models, we have got a quite good understanding that how the flexibility should be modeled so that it has a value. Warsila vision, it's I think pretty much the same what each technology company today have toward 100% renewable future. Why is that? Of course, this is, I think, very obvious that actually the price of the wind and solar is coming down, so it starts to be, and it's already cheaper than thermal power plants in the countries. This is a forecast from the Bloomberg, where we see that this is China, so that where the offshore wind and offshore and onshore wind is cheaper than the new build combined cycle and the coal capacity. And the same for solar and those thermal capacities. And the same trend is for the US. So it starts to be cheaper than the thermal capacity in the power system. Then, if when we start to move towards these 100% renewable cases, what kind of challenges and opportunities there is for those kind of systems? It depends, of course, a lot where you are located. In some countries, you have a lot of solar resources, and that should and will be the main source of electricity. In some countries, you have hydro, wind, and in some countries it is a mix of these different technologies. And what is now the main reason? What is the challenge of having different technologies as a main source? Because there is also a seasonality for those energy sources. For solar in the equator, okay, it's almost every day when you get the solar output. But then solar in Germany, for example, it's totally different. You can get the full energy during the summertime, but then in winter time, you can rely on solar in that kind of areas. But so the role of flexibility then. because you have different kind of challenges based on the resources you have in the country or in the location. So on the daily level, you need to have flexibility. Typically, that is done or could be done by hydro or batteries. This is a one dispatch example where from 100% renewable power system, where you have solar and you exceed the demand, and then you store it in a battery, and then in the nighttime you discharge the batteries. So this kind of systems, batteries and the solar is a good match. But then when you go on and you have some seasonality on the weekly level, and you, for example, don't have solar available there, then it's again hydro, batteries, but then you need to store the power in some other forms as well, and this power to gas is a good option, or one option for that one. And in this presentation I will show a case example that how it can be done. In this example now we see that there is wind production for 1 week, and then actually you need to have some thermal capacity providing some electricity at some point. This is on the weekly basis, but then on the seasonal level, you need, as I said, you need to kind of convert the power to some kind of other form of energy, and this power to gas and LNG start to play a big role there, because the lithium-ion batteries, for example, you can store energy that long time, and it costs very, very much. This is a weekly energy profile from Germany, where we see that in the winter time actually the solar does not produce that much energy at all. In the winter time, in the summertime it provides, but then also there is some variability on the wind monthly production. What is the role of technologies in these energy transitions? I just told that there is actually a need for flexibility. There is this renewable energy, inflexible generation, and flexible generation, and energy storage. And if in the power system you have different amount of renewables, then of course the role of these technologies is different. So today, this 20% is something that many countries are having today, and it's not causing that much issues for the fleet. And then all these technologies can play a role there. But when the renewable starts to hit 50 or 80% actually, then this inflexible thermal capacity starts to have really big problems to serve. And then this 100% renewable power system means that actually there is no need for this inflexible thermal generation at all. And in this case study now, we just looked at this 100% renewable case. So we are not now talking about this path, that how we really can get there, but what is kind of optimal solution. 100% system case study. So the resources for the renewables are biomass, hydro, solar, wind, geothermal, the main sources I would say. But in this case we wanted to simplify this a little bit, so we just took wind and solar. Energy goes to demand, and then we have batteries there which can balance on the daily, maybe on the weekly level. And then we have this power to gas option in Plexos, where excess electricity is converted to the gas, and then it's stored in the LNG and then used in a flexible thermal power plants. On top of that, there is certain efficiencies, of course, for those power to gas process. And then on top of that, of course, there is energy that you can't use, and then it goes to somewhere. We were discussing this morning the coupling the sectors, but in this study we didn't now consider that actually there is any value of this excess energy. It's just kind of curtailed and not used, just increasing the levelized cost of electricity for the system. So how the model looks like. So we did a simple model. It's generic green fleet greenfield Plexus LT model for 1 year. We took year 2030 with hourly dispatch. It's energy-only model, so we didn't consider any reserves or anything in that. We took 2 countries or 2 profiles. We took Senegal, which has a monthly profiles. In the model we had hourly profiles, but this is just illustrating you that actually what is the seasonality of different resources in Senegal. There is a wind production in the beginning of the year, but then after the summer actually the wind is not blowing in the country, which means that you would need to provide energy somewhere else. And then demand is also increasing at the same time. And for a Germany, a little bit different kind of seasonality, no solar in winter time, some seasonality on the wind and demand as well. So we did both of these profiles. Then we run 3 different scenarios. In the first scenario, there is solar and battery available for Plexus to build. And second one, we have solar, wind, and battery. And then the third one, we had solar, wind, battery, plus this power to gas with flexible thermal capacity. So the new candidates for the Plexus to build in the LT model was the solar and wind batteries and the power to gas with flexible thermal. How this was set up in Plexus? Some technical stuff. So it's very simple model: solar, wind, engine power plant, and power to gas converter as a generator. When we are producing gas, actually, so we used gas module in this beside the power module in Plexus. This power to gas converter acts as a anti-generator there, which means that it's linked to gas field power to gas through a constrained power to gas link, which means that every time this power to gas converter generates or actually consumes, then it creates some gas on the gas field. And then for that one we have created a quite simple manual constraint. And then this power to gas field is connected to the gas node, and then gas node is connected to the gas storage. And when we want to consume that, then actually it goes up again to gas node, and then the gas node is connected to fuel, power to gas, or synthetic gas, if you want to name it that way. And then that that fuel is then connected to the thermal generator, which can use the fuel. So about the results, we have 6 scenarios. Senegal, Germany. First of all, the y-axis is percentage of peak demand. It's down here. We see that solar and battery in Germany requires quite a lot of capacity to be built. So let's change the scale a little bit. So actually it doesn't make much sense. So the same picture, but we scaled this a little bit down. So what we can see here is that on the Senegal case, where actually the solar was, I would say, more attractive because there was no seasonality on solar as such, and also the solar conditions are better in Senegal. It builds a lot of solar, but also here in the solar plus wind plus batteries, it builds some wind as well, because it wants to kind of the least cost optimization wants to get the optimal mix of the result. And then if we allow Plexus to build this power to gas, we see that actually it goes even more down. And in the model we had 8-hour lithium-ion batteries and 4-hour lithium-ion batteries. What happens actually? So it now splits it to the two categories as well, which means that actually this power to gas, which we can see here, it's kind of taking care of this longer duration storage. For Germany, a little bit different kind of results. What is the main difference actually is that in Senegal the solar is the dominant, and then in the Germany the wind is the dominant source of electricity. Thermal capacity of those flexible thermal power plants in this when the power to gas is available, it's around 12%. It's not much, but it's enough to let Plexus to build much less wind and solar, because you can store energy in these fuel storages. And yeah, actually we can see it in the coming slides better. So the energy, case study energy, 100% of the demand is here. How much energy is generated? It's a little bit more than the 100% because there are losses. Power to gas process actually is not that effective, so the efficiency is quite low, so it means that actually you need to produce more than what is the generation. But then when we start to look at curtailed energy, in the case Germany, with solar, it's actually a lot of energy you are curtailing, because it doesn't, otherwise it's not possible to use that source as the only source. Interestingly, also we see that the curtailment goes down quite a bit when you can use this power to gas converter there to store the energy. And looking at the LCOEs, so what is the system total costs? It considers now the capital cost and all the operational costs. Almost $400 per megawatt hour system cost if just using solar and batteries in Germany. In Senegal, the same is 108, which is actually not that much if you consider that you are using, for example, HFO in Senegal. It is more than 100. What is the levelized cost of electricity? And using power to gas, we can get down to $70 per megawatt hour. How does it look then? If you look at the dispatch, I said that this power to gas is used for storing or handling the seasonality of the power system. So this graph shows that on that 1 year, how much energy is actually stored in the fuel storage. So it is around 10 or 12% of the annual energy needed, what you need to store. You remember that it was after summer when the wind profile went down, which means that actually at that time you start to use that fuel what you have on the LNG tanks. And then back here at the end of the year you start to collect the energy, so that at the same after the summer you can again start to use it. How does it look? If you look one week there, what we can see, there is solar of course, but if you look at this line, it's increasing, and now the power to gas converter is this line here. So it's running flat out here, just collecting energy to the gas tank for the need in the later of the year. And during this week, actually, when you are using that energy, we see that the power to gas converter is not used, but then this orange one, which is the flexible thermal capacity, it's then filling the gaps in the evenings and the nights when the solar is not there. Also, you still, of course, you store, you charge your batteries in the daytime when the solar is there, and you discharge it in the night, but it's not enough, and that's the optimal solution actually to use this power to gas. Same for Germany. It was 11% or something of the demand, but in this case it is around 5% only, because there's not that much seasonality on the resources in Germany. I did a model with solar and power to gas for Germany, and it was 40% of energy of annual demand you need to store in the gas storage tanks, because of course in the winter time there is no solar available, then you need to, in the summertime you need to take all the energy in your tanks and then consume it during the winter time. But similar kind of graphs for the Germany. So for 1 week example here, actually this goes down, which means that you are using your gas, which is this orange area. You have some wind, but during that week actually wind is not blowing. So you need to have some seasonal storage available. And taking one example here, in the summertime, when you have actually quite a lot of solar available, you are hitting the peak demand with this solar, but still you store some wind during these first 2 days, and then you are consuming it here on the evening or the night of the coming days. Then last slide, showing now what we can learn from this kind of simple exercise actually. Based on these profiles now, so it is 2.5 times the peak demand actually you need to have solar in the Senegal, for example, and 1 times peak demand wind. 0.4 times flexible thermal capacity, and the similar kind of results for the Germany. And as we can see, solar and wind are the kind of different, have a different role in these different kind of systems. So in Germany, the solar is not the best option, and that's why wind is selected. And looking at how much of annual demand you need to store in a tank, in Senegal it's 14% because of seasonality of the renewable resources. And in Germany, because the wind is the main source and it's windy almost all around the year, then actually it's not that much, it's only 5% of the annual demand. Then the power to gas converter, this is now, this means that how many megawatts you can take electricity out and then convert it to. So it's only, okay, only, but it's the same 0.4 and 0.7 times the peak demand of the system. Which actually tells us the thing that wind requires more this power to gas seasonal, because solar typically is producing at the daytime, and then the batteries are the better friend of the solar resources. But calculating now based on this simple model that what is actually the system LCOE in these models, it was around $75 per megawatt hour, which is, I think, not that much. Okay, the model is simplified, energy-only model, but gives us some ideas about this, how the future power systems could look like.